Okay, so we discuss about the different types of wears. Now, next we discuss under sluices. So you can see here that this is under sluice. This portion here, this is the under sluice portion of the wear. Under sluice portion of the wear. So in this case, you can see here that length divided into ways by pairs. Each way is provided with a gate is to act as opening of controlled height. So it means that this portion, under sluice portion of wear, length are divided into ways by pairs. Each way is provided with a gate is to act as opening of controlled height. So let us study this in detail, that the crust level of under sluices is lower than that of the wear. So this is the wear. Now we have covered this portion here. Clear? Now we discuss the under sluices. So under sluices, these are also known as covering sluices because the sediments which are accumulated that are flushed downstream through the under sluices. That's why these are also known as covering sluices. So it is a deep channel in front of the head regulator, that is canal head regulator. You can see here that it is in front of this canal head regulator. This is canal head regulator. So it is a deep channel in front of head regulator and dispose of heavy silt and a part of flood discharge onto the downstream of the barrage or wear. It creates less turbulent pockets of water near the canal head regulator. A divide wall separates the main wear portion from the under sluices portion of the wear. You can see here that the divide wall, it separates the under sluice portion of the wear from the normal wear portion, that is wear proper or main wear. So the divide wall separates the main wear portion from the under sluices portion of the wear. The crust of the under sluices portion of the wear is kept at a lower level than the crust of the normal portion of the wear. The under sluiced length of wear or barrage is divided into a number of ways by pairs with separate gates. So what are the functions of covering sluices? To draw water during dry weather flow. When the water in the river that is low, so these under sluices or covering sluices, they function to draw water during dry weather flow. You see that at the bottom, these gates are provided here. You see land divided into ways by pairs. Each way is provided with a gate is to act as opening of controlled height. So that is why the function can be to draw water during a dry weather flow. I will show you in the picture also. To reduce flow of silt into canal head regulator, therefore also called covering sluices. So these under sluices, they help to reduce the flow of silt into canal head regulator. To scour the silt deposits in the pockets periodically, because it helps to reduce the silt into the canal head regulator, so that silt that is deposited in front of the scouring sluices or under sluices, if the gates are closed or if the gates are open, that silts, these are released by opening of the gates of the under sluices. So if the gates are closed, the silts will be deposited, and then the gates are open, the water along with the silts will be flushed to the downstream side. So these are the functions of the under sluices. You can see important component of diversion headworks. I will show you the pictures. So in this case, you can see that these are just at the bottom tunnels or gates, clear, rectangular or circular. You can see here, these are under sluices. So even if the water level in the river is low, still the water can flow. So that's why the function was to draw water during a dry weather flow. To reduce the silt into the canal head regulator, this I will explain later in detail. I'll show you the picture. Even here you can see that these are in the form of these tunnels here, which are basically silt excluder. So the silt along with the water flows here, and then these gates are opened and the silted water is flushed downstream of the river. So these are under sluices or scouring sluices. You can see here that we have this weir, but at this point we have this sluice. So the silt which is deposited, that will move along with the water to the downstream side of the weir. That's why this is known as a scouring sluice. So you can see here that in this figure, this is the normal weir here, this portion. So the water will just flow over this weir. But in case here at the bottom, you see that gates are provided and the water can flow and it will flush the sediments here. So the sediment, the silted water will be flushed here through these under sluices, and silt free water will flow into the off-taking canal. So this is under sluices. You can see the importance components of diversion headworks. Now you can see here, this is a video. You see here that we have this canal head. This is canal head regulator. These are the gates of the canal head regulator. So you can see controlled supply can flow into the canal. So these gates can be operated manually or through a motor. Mechanically, it can be lowered and raised. This is silt excluder. We will study this in detail. So you see the silt that will be carried by the lower layers of the water. So that silted water will enter into these tunnels, and above layers will be having relatively less silt that will be allowed to flow to the canal. And you can see here that through these tunnels you can see the gates. You see the gates are open. These are under sluices. So by opening these under sluices, gates, the silted water can move to the downstream side. So in the canal, clear water, relatively silt-free water will flow. You can see here these are under sluice gates. When these are open, the silt can be flushed downstream. These are under sluices. Now next we discuss the fish ladder. Now the fish ladder is here, this portion here you can see. This is the fish ladder. So as we know that fish move from upstream to downstream in search of relatively warm water in the beginning of winter and return to upstream for clear water before the onset of monsoons. We have the flood water, so they try to move to the clear water upstream. The fish ladder is provided just by the side of the divide wall for the free movement of fishes. You can see here that in the divide wall, this is the plane from the top. This is plane of a typical fish ladder. So these baffle walls are provided to slow down the water. Clear? So that fish can easily move from upstream to downstream and downstream to upstream. In the fish ladder, the optimum velocity is 6 to 8 foot per second or 2 to 2.5 meter per second. This is the optimum velocity. It is designed for this velocity so that the fish can conveniently move from upstream to downstream and downstream to upstream. So this low velocity that is obtained by baffle walls. As you can see here, these are baffle walls. So the low velocity is obtained by these baffle walls. Now these are the different photographs of the fish ladder that are provided. You can see here that the fish will move from upstream to downstream and vice versa. So these are fish ladder. We have to provide them so that not to disturb the biodiversity of the rivers. You can see here, this is the concept that the fish can move if we can provide this fish ladder. Clear? Now here in this video you can watch So you can see that when we provide these hydraulic structures, we block the passage of the fish. So these fish ladders, these are provided for migration of fish. Next, we discuss the divide wall. So this is the divide wall. You can see here that it divides the undersluices portion from the main weir portion, and also it acts as one of the side wall of the fish ladder. So this is the divide wall. You can see here, this is the divide wall. The divide wall is a masonry or a concrete wall constructed at right angle to the axis of the weir and separates the weir proper from the undersluices. If there are two canals of taking from each flank, then there will be two divide walls and two undersluices. Clear? For example, in this picture here, you can see that there is one canal. So you have divide wall and undersluice. If we have another canal from the other side, then again there will be undersluice portion and another divide wall, as I will show you later on in the picture. So if there are two canals of taking from each flank, then there will be two divide walls and two undersluices. The top width of divide wall is about 1.5 meter to 2.5 meter. Its length on the upstream side should be sufficient to keep the heavy turbulence at the nose here, to keep this heavy turbulence at the nose of the wall well away from the upstream protection of the sluices. So its length on the upstream side should be sufficient to keep the heavy turbulence at the nose of the wall well away from the upstream portion of the sluices. Its length on the downstream side should extend to cover the hydraulic jump and the resulting turbulence. So you can see here that it has length on the upstream side as well as on the downstream side. The main functions served by divide wall are: the floor level of the undersluices is generally kept lower than the floor level of the main weir. Hence, a divide wall is essential to separate the two floors. This prevents the turbulence action. So you can see very important function of the divide wall, that the floor level of the undersluices is generally kept lower, as you saw in the video also, than the floor level of the main weir. Hence, a divide wall is essential to separate the two floors. This prevents the turbulence action. It helps in providing a comparatively less turbulent pocket near the canal head regulator, resulting in deposition of silt in this pocket, and thus to help in the entry of silt-free water into the canal. So you can see that this is another important function. It helps in providing less turbulent pocket near the canal head regulator. Divide wall may keep the cross currents, if formed in the river, away from the weir. Cross currents lead to vortices and deep covers. For this purpose, additional divide walls are sometimes provided. This is an example. You can see that where more divide walls are provided, and the idea is to keep this cross currents, if formed, away from the weir. Why? Because these cross currents lead to vortices and deep covers. So you can see that additional divide walls sometimes may be provided. You see, these divide walls, cross current kept away from weir by these divide walls, and to serve as the side wall of the fish ladder. So you can see that incidentally this divide wall, it serves as one of the side of the fish ladder. Next we have river training works. So river training works are required near the weir site in order to ensure a smooth and axial flow of water. That is, we train the river. These are required, river training works are required near the weir side, barrage side, in order to ensure a smooth and axial flow of water, and thus to prevent the river from outflaking the works due to change in its course. So you see, we direct the water towards the hydraulic structure because the river can change its course. The river training works required on canal headworks are guide banks, marginal bunds, spurs or groins. So you can see here, this is the figure layout of a barrage. As we studied here about the divide wall, that if there are two canals of taking from each flank, then there will be two divide walls and two under sluices. So you can see here in this figure that we have this canal here. So we have these under sluices, and we have this as the divide wall. And we have another canal here. So we have under sluices here, and we have another divide wall here. So if there are two canals of taking, then there are two under sluices and divide walls. And in between we have the weir proper or the barrage section. Clear? This all is barrage section here, but this is the main weir. So that is in between now here. So coming to the river training works. So you see here this guide bank and marginal bunds. So the idea is that these are required near the weir site in order to ensure a smooth and axial flow of water. Clear? So what are guide banks? The guide banks force the river into a restricted channel, and thus ensuring a smooth and an almost axial flow near the weir or barrage site. You can see here that if I take a section here, how these guide banks, these are just embankments. You can see here guide bank details. These guide banks which are shown here. So if I take a section here, this is section AA, this is section AA here, you take a section here. This is section AA. You see, these are just embankments. So these are protected by these stone apron, stone pitching layer. Similarly, a section BB taken here. So again, you can see that these are just these embankments. So we have the high flood level and a freeboard is provided not to overtop this structure. So these guide banks force the river into a restricted channel. You see the guide bank here and the guide bank here. So the water is restricted into the channel. The second one is marginal bunds. This is marginal bund. So marginal bunds are flood embankments in continuation of guide banks designed to contain the floods within the floodplain of the river. So marginal bunds are flood embankments that are designed to contain floods within the floodplain of the river. Both height and length vary according to backwater effect that we just discussed, because construction of a barrage and where it will raise the water level. So both height and length vary according to backwater effect caused by the barrage or wear. Marginal bunds partially help in controlling and guiding the river flow between the guide banks. Partially help in controlling and guiding the river flow between the guide banks. For this reason, the length of guide banks do depend on the layout of the marginal bunds. Length of the guide banks, these are the guide banks, do depend on the layout of the marginal bunds. Marginal bunds are nothing but earthen embankments protected by groins wherever needed. Just like you see here, embankments for the guide banks, same for the marginal bunds. So these are earthen embankments protected by groins wherever needed. So next we discuss the spurs or groins. Groins are the embankment type structures constructed transverse to the river flow, extending from the bank into the river. These groins are also known as spurs, dikes, and transverse dikes. So these spurs or groins are nothing but these are just embankment type structures constructed transverse to the river flow. You see, this is groin here. This is groin extending from the bank into the river. And why we provide these spurs or groins? To protect the bank. You see, the water is pushed towards the center, so it protects the banks of the river against erosion. And that's why these spurs or groins not only provided in the rivers, but they can also be provided on the coasts, sea coasts, ocean coasts, to provide protection against erosion. You can see here in this photo, these are spurs or groins. These are embankment type structures and they just protect the banks of the river or the coasts, sea coasts or ocean coasts, against erosion. Purpose of a groin, as I already explained, contracts a river channel to improve its depth. You can see here it pushes the water towards the center, so contracts a river channel to improve its depth. Protects the river bank. Silts up the area in the vicinity by creating a slake flow. You see here that the water here will become very slow, so silt will get a chance to be deposited here. So the purpose of a groin or spur is also that silts up the area in the vicinity by creating a slake flow. So the water here, it will be unaffected by the main water currents of the river, so the silt will get a chance to be deposited. If you remember this, we already discussed also spurs. In case of internal silting system, clear, to strengthen the banks of the canals, as we discussed in the previous lecture, and trains the flow along a certain course. So you can see here that it directs the flow along a certain course. So these are spurs or groins. You can see here these are groins. So the purpose is the functions that we already discussed, and it protects the banks against erosion. You can see here this is groin or spurs. Types of groins. Classification according to materials of construction. We can have permeable groin, we can have solid impermeable groin. Classification according to its height below high water. It can be submerged groin or it can be non-submerged groin. Classification according to function it serves. It can be attracting groin, it can be deflecting groin, it can be repelling groin, and can be sedimenting groin. So there are different types. Clear, as you can see here, this is an example of repelling groin. You see here silt pocket, silt will be deposited here. A scour hole will be created here because the water, it will form vortices here as it moves. So we can discuss a full design of these spurs or groins. Clear, how to avoid these scour hole. But anyhow, this is repelling groin. And also this is an example of attracting groin. You see 50 to, this is 60 to 80 degree in the direction of the flow. Clear, it makes with this here bank of the river. So now you can see that the scour hole, it is now shifted here downstream. And also we have some special types of groins that include T-headed groin. That will be a groin that will be in the form of T-headed. Or hockey type groin, that will be in the form of a hockey type like this. And Burma type groin. So we can discuss this in detail, the design of groins also. Clear? But anyhow, just here we briefly discuss them as components of diversion headworks. But these are essentially river training works. Clear? So this is another example of spurs or groins. Clear? Earthen embankments. You can see here the spurs and groins which are provided. The functions we already discussed in detail. So protects basically the banks of the river against the erosion. So this is another picture. Next we discuss canal head regulator. So this is canal head regulator here. So canal head regulator with gated openings called the head sluices. So it controls the flow of water into the canal. That is why it is known as canal head regulator. So a canal head regulator is provided at the head of the off-taking canal and serves the following functions. You can see here that we have off-taking canal. We have this weir proper. Then we have the fish ladder here. This is the divide wall. We have the under sluice portion here that we discussed. And we have these canal head regulators. This will be a gated structure. And by operation of the gates, the flow of water is controlled into the off-taking canal. And it is stated that for best conditions, this angle should be 90 degree to 110 degree. This is for best conditions. This angle should be 90 to 110 degree. It regulates the supply of water entering the canal. It controls the entry of silt in the canal. And it prevents the river floods from entering the canal. Because if we do not have this regulator, and if flood water comes, then there will be no control to restrict the flood water entering into the canal. So this is a gated structure provided. So it prevents the river floods from entering the canal. So this is a typical section through the canal head regulator. This is a typical section. You take a section here. A typical section is taken here. This is what is shown here, a typical section through a canal head regulator. So you can see here, we have a deck slab bridge resting over the piers. We have the piers, a gated structure. And this is the upstream. The water will flow in this direction here. And this is the downstream. So the water will move through the gated structure into the canal downstream. So you can see, because the water moves, so at this point you can see that protection is provided in the canal bed against the uplift pressure as well as the scouring. This is for the canal head regulator. And then once the canal head regulator allows the water to pass through, then after that the water flows in the canal, that we already discussed in the previous lectures. Now in this case you can see the canal head regulator. You see this is head regulator. So the gates are provided and the flow is controlled by opening and closing the gates, either can be manually or mechanically. So by lowering or raising the gates, the water is controlled into the canal. So you can see the downstream. So this is silt excluder. So this we will study later in detail. You see the silted water will flow or enter into these tunnels, and the silt free water above that will be allowed to enter into the canal. Because the main function is that the silt that is carried by the water in the lower layers. So that is why in this case you saw that the tunnels, the water, silted water will enter into the tunnels, and the silt free or relatively less silted water that will be allowed to enter into the canal through the head regulator. So now we discuss the silt regulation works. The entry of silt into a canal which takes off from a headworks can be reduced by constructed certain special works called silt control works. So the entry of silt into a canal which takes off from the headworks can be reduced by certain special works. These are known as silt control works. So we have basically two types of silt regulation works. We have silt excluders, which you just saw in the previous slide in the video, and we have silt ejectors. So silt excluders. Silt excluders are those works which are constructed on the bed of the river upstream of the head regulator. The clearer water enters the head regulator and the silted water enters the silt excluder. In this type of works, the silt is therefore removed from the water before it enters the canal. The fundamental principle behind silt control is that most of silt tries to settle down in water, thus confining itself mostly in the bottom layers of water. So this is the fundamental principle, that when silt is carried in water, so silt try to settle down, thus confining itself mostly in the bottom layers of the water. So if we can separate the bottom layer of the water from the top layer, and the top layer relatively silt free, that is allowed in the canal. So the silt excluder, that is based on this principle. The silt excluder is a device constructed in the river bed just upstream of the regulator to exclude silt from water entering the canal. It is so designed that the top and bottom layers of flow are separated, with the least possible disturbance, the top sediment-free water being led towards the canal, while the bottom sediment-laden water is discharged downstream of the diversion structure through the undersluices, as you already saw in the video. The device basically consists of a number of tunnels in the floor of the deep pocket of the river, isolated by a divide wall. The sill level of the regulator is kept the same as that of the top level of the RCC or roof slab of the tunnel. The capacity of the tunnels of these silt excluders is usually kept at about 20% of the canal discharge, and they are designed to maintain a minimum velocity of 2 to 3 meters per second to avoid deposition in tunnels. 2 to 3 meters per second, the silt will not deposit, and it will be flushed through the undersluices to the downstream side. So you can see here that these are tunnels, If I show you this picture here, you see that these are the tunnels. So the fundamental principle is that when the water flows, the silt is carried by the lower layers of the water. So those lower layers are separated. You can see that the sill of the regulator is same as the roof slab, that is RCC slab of the excluder, silt excluder. So silt excluder is constructed on the bed of the river upstream of the canal. So the clear water, it will be then allowed to enter into the canal. So this will be clear water or relatively silt free. Clear? Relatively silt free. And silted water, that will be entering into the silt excluder. So this is silt excluder, and this water, then it will be through under sluices gates, it will be flushed to the downstream side of the weir or barrage. So this is the main idea here. Clear? Now you can see here, this is the head regulator, and these tunnels, you can see this is silt excluder. So the silted water will enter into these tunnels. So the lower part of the flow that carries the silt, so that will enter into these tunnels. And the upper layers of water, relatively silt free, that will be allowed to enter into the canal. And you can see the under sluice gates. You can see the under sluice gates. So if they are open, the silted water that is discharged to the downstream. So the clean water or relatively silt-free water will flow into the canal. This is what you can see here, a view of the completed silt excluder at Tonsa barrage in Pakistan. You can see here that it is constructed in the river bed upstream of the regulator. So the silted water will enter into these tunnels. These tunnels can be up to some portion or can extend up to the divide wall. So the basic principle, as I already explained, is that the lower layers of the water carry the silt. So that will enter into the silt excluder tunnel, and you can see the gates are open, so that can be flushed to the downstream side. And the upper layers, that water will be allowed to enter into the canal head regulator. So this is what you see here in this picture. So the water is coming in this direction here. The silted water will enter into these tunnels and move downstream, and the silt-free water that will enter into the canal. So you can see the silt excluder that is provided on the river bed upstream of the canal head regulator. This is another picture. You can see that again the silted water will enter into the tunnel, and that will be flushed here by opening gates of the under sluices. So you can see the importance of under sluices, and the relatively silt free water that will enter into the canal head regulator and will flow into the canal. So this is a measure to control the silt into the canals. The second one is silt ejectors. So silt ejectors, they are constructed actually in the canal. Clear? The silt excluders, they are on a river bed upstream of the canal head regulator. So in case of silt regulator excluder, this silt excluder, the silt is removed from the water before it enters into the canal. Whereas in case of silt ejector, the silt is removed from water after it enters into the canal. So this is known as silt ejectors. So silt ejectors, also called silt extractors, are those devices which extract the silt from the canal water after the silted water has traveled a certain distance in the off-take canal. So you see, this is the difference. In the silt excluder, the silt is removed from the water before the water enters into the canal. And silt ejectors or silt extractors are those devices which extract the silt from the canal water after the silted water has traveled a certain distance in the off-take canal. So this is actually constructed on the bed of the canal. So again, the bottom layer, it will enter into these tunnels and the silt-free water will continue to flow in the canal. And this silted water, they will move through the escape channel and it can again join the river downstream. I will show you in another picture. So these works are therefore constructed on the bed of canal and a little distance downstream from the head regulator. So silt ejectors or silt extractors, they are constructed on the bed of the canal. Silt excluders on the bed of the river before the water enters into the canal. And silt ejectors, they are constructed on the bed of canal a little distance downstream from the head regulator. Now remember one point at this stage, that now silt excluders are better or silt ejectors are better. Now in silt excluder, if you can see here, if I go back to this picture here, now we have the river water which is coming here, we have the divide wall on this side, we have the under sluices, you can see here, portion here, and then the canal head regulator. So now in this case, to achieve a relatively uniform layers, that is upper clear water layer and lower silted water, heavy silted layer, that is difficult to achieve here compared to the silt ejector or silt extractor. Because when the water is flowing, this is the silted water, when it is flowing in a canal, then it tries to become a uniform. Clear? Because in the canal there is no disturbance, as you can see here in this picture for silt excluder. So a relatively uniform water layers can move in the canal with the bottom silted water more silt carrying and the top relatively less silted water that can be easily efficiently separated by silt ejectors. So silt ejectors are therefore superior to silt excluders. Silt ejectors are better than the silt excluders. But you can see here that this arrangement to be provided in the bed, and then you see this escape channel to be provided. So silt ejectors are more costly as compared to silt excluders. You can see here the water moves in the canal and then these tunnels are provided. So the silted water, it will move into these tunnels and then moves into the escape channel, and the relatively silt-free water, it can continue to move in the canal. So you can see here that this is the section. This slope is provided, so silt water will enter into these tunnels and relatively silt-free water will continue to flow into the canal. So these are properly designed, clear? This is what you see here. So you can see that after we provide this silt ejector, then the same water, that is silted water, it can move through this escape channel and again can join the river downstream of the diversion headworks. So that is why this arrangement here, you see that this arrangement is better as compared to silt excluder, but it is more expensive. Clear? Because you see here you have to provide this arrangement, so this is more expensive. But remember, silt ejector, that is more efficient as compared to silt excluder. Next, we discuss site selection for diversion headworks. So we discuss the components and their functions of diversion headworks. Next, we select site selection for diversion headworks. The site for headwork should be selected after giving proper consideration to the following points. How we will select site for these diversion headworks. So we have to consider different points: economic considerations. The construction materials should be available in large quantities in close proximity of the site. At the site, the river section should be preferably narrow, because otherwise the length of the weir and barrage will be more, that will add up to the cost. So at the site, the river section should be preferably narrow and straight with high non-submersible banks. The banks should be sufficient, should not be submerged. Non-submersible banks. It reduces the cost of river training work that we just discussed. Guide banks, marginal bunds, spurs, groins. The cost of connecting the site by rail and roadway should be less. So communication, it should be easily accessible, the site. To reduce the cost of construction of the canal system, the site should be close to the cultivable area. So where we want to construct this barrage or this diversion headworks, because we raise the water level and divert the water into the canals. So to reduce the cost of construction of the canal system, this site of the barrage or the diversion headwork should be close to the agricultural fields. Otherwise, then we have to provide very long canals to reach the water from the diversion point to the agricultural fields. Number of cross drainage works required to be constructed should be minimum. So cross drainage works we will discuss as a separate chapter, but I already explained in the previous lectures that whenever the canal it crosses a natural drain, then we have to provide the cross drainage works, again hydraulic structures. So to reduce the cost, the number of cross drainage works required to be constructed should be minimum. Functional considerations: moderate height of the obstruction, that is the weir or barrage, should give good command. So far as possible, the canal takeoff should be at right angles to the river. We already discussed this in detail, 90 to 110 degree. That is the best. The river reach should have central flow without tendency of scouring or silting. Without tendency of scouring or silting. The canal should give maximum command. That is, the off-taking canal should supply water to maximum area that can be covered. And the third one, structural considerations. Good foundation should be available at moderate depth. So we have to provide foundation for the barrage or weir or these diversion headworks. You see this canal head regulator that the water flows into the canal and this barrage or weir. So good foundation should be available at the site at moderate depth. Similarly, the following consideration should be kept in mind while selecting the site for a barrage or weir. So this was one criteria that we discuss while selecting site for a diversion headwork. Now this second is taken, this discussion is taken from the book by Dr. Iqbal Ali, Irrigation and Hydraulic Structures, Theory, Design and Practice. So the following considerations should be kept in mind while selecting site for a barrage or weir, because barrages are nowadays constructed, so mostly our focus will be that on barrage as compared to the weir. So the site must have a good command over the area to be irrigated, and also must not be too far distance to avoid long feeder channels. The width of the river at the site should be preferably minimum with a well-defined and stable river reach. A good land approach to the site will reduce expenses of transportation and the ultimate cost of the project. So these are easy, these points are easy to understand. There must be easy diversion of the river after construction. Existence of central approach of the river to the barrage after diversion. This is essential for proper silt control. If it is intended to convert the existing inundation canals into perennial canals, inundation canal we already discussed, where the water flows during flood condition, perennial canal where throughout the year the water is available. Site selection is limited by the position of the head regulator and the alignment of the existing inundation canals. You see, the following points should be kept in mind when we select site for diversion headworks. A rock foundation is the best, but in the alluvial plain the bed is invariably sandy. So rock foundation is the best, solid foundation, clear? Now the common practice in Pakistan has been to build the barrage on a dry land in a by river, and after completion to divert the river through it. So what we do is that we have a river and then we have a by river. For example, if I can draw the figure, you have this river here and there can be a by river, clear, or dry land. So the water can flow here the water can flow in this river. Now in this place we can construct the diversion headwork, barrage or weir on a dry land in the Abai river. So we have, this is the river, because if you want to construct you have to divert the river then, clear? So the common practice in Pakistan has been to build the barrage on a dry land in Abai river. So in a dry land you construct the barrage. Let me just increase the width here. and after completion to divert the river through it. And then after completion, the river can be diverted here. This gave an oblique approach and created many problems. Like you can see here that we have this headworks axis, and then we have this as the river axis. So it makes an angle. So this gave an oblique approach and created many problems. So the following guidelines have now been proposed by the Irrigation Research Institute in Lahore. Their recommendations are based on extensive hydraulic model experiments for each individual case. So to avoid this problem here, then model studies were conducted by Irrigation Research Institute Lahore, and they give recommendations. So what are these? Where the angle between the headwork axis and the river axis exceeds 10 degree, this angle here, the problem arises of concentration of flow on one side and island formation within the guide banks on the other side occurs. You see, if the water is flowing in a river and the water is concentrating on one side, what will happen on this side? Island will form. Material, you see, island will form on the other side because the water is pushing along this side here, concentrated on this side here. So the problem arises of concentration of flow on one side and island formation within the guide banks on the other side occurs due to heavy silting, as in case of Islam, Sidnai and Balochi barrages in Pakistan. So you see, we are learning from experience. If the river axis is to the right of the headworks axis, the concentration of flow is generally on the left side. With the consequent tendency to form an island on the right and vice versa. When a barrage is located below the confluence of two rivers, now two rivers meet, it should be located sufficiently far below the confluence and concentration must be given as to which of the rivers dominate the confluence. So the site should be located sufficiently far below the confluence and consideration must be given as to which of the rivers dominate the confluence. The barrage should be located as far as possible in the center of the floodplain. Asymmetry of location increases the likelihood shoal forming and calls for expensive training works. Shoal forming, because you see here, this is the river here, and we have this barrage we construct or where. So you see that on the upstream side there will be some small islands that the water will flow here. So these are shoal forming and calls for expensive river training works. So these are, the points which should be kept in mind while selecting site for diversion headworks. Similarly, there can be another discussion that when the river flows, there are 4 stages. You see, we have the mountains where the river starts. So in this range, when the river starts, although it can provide a rock foundation to the diversion headworks, but you see that in the hilly area, normally we do not have the agricultural fields. So that's why at this stage, the rocky stage, clear, or mountainous part of the river, this is not fit for construction of diversion headworks. Now when this river flows, then you see that we have submountainous range where you see large boulders are placed. Downstream of the mountains, then we have this second stage. So in this case, we can call it as submountaneous. So here it can be that at this stage we can construct diversion headwork. Then after this we have the plains. So the third stage of the river where we have the plains. Again, here the diversion headworks can be constructed. And the fourth is that we have deltaic region where it joins the sea. You see that we have this sea and it continues. When the river joins the sea, ocean. Now at this stage we have the fourth stage. That is a deltaic. Deltaic region. Now in this case you normally see that if I draw the plane at this point here, so what we observe here that the deltas which are formed, the river is like this. When it joins, you see deltas are formed here. And it joins the ocean. So again at this stage it is not appropriate to construct the diversion headworks here. So that is why in the submountainous region or the plains, they are best suitable for construction of diversion headworks. You can find the detail about this from the irrigation books by Pumia. Now the most suitable site for a barrage when constructed on dry land is below the outer side of the convex bund, which is followed by the straight reach of the river. So these are the points that we should keep in mind while selecting site for a diversion headworks. Next, we discuss a case study that is Amandara headworks that we have in our province. You see that we have this Suat river that is flowing, and it is flowing in this direction. So we have this Amandara headworks that is near Batkhela. So from this headworks you can see here This is the canal head regulator, and the water is diverted into this canal. This is the flood plain. You can see the water also flows here. It can flow similarly during flood. The water can flow here, and it can again join the river here. So this is Amandara headworks. You might have visited there. So this is canal head regulator, and the water is diverted to this off-taking canal. You can see here we have the agricultural fields. This is that off-taking canal. This is the canal head regulator. This is the Suwat river that flows in this direction here. And you can see the agricultural fields on both sides. This is the close picture here. So this is how the water flows. Clear? So this is part of the where the water flows downstream. These are, you can see the baffle blocks to dissipate the energy. This is the river floodplain, and this is the canal head regulator. And this is the canal. The water flows in this canal. This is what you see here. This is canal head regulator. This is canal. This is now the close picture here. So this is canal. And this is, we have Suwat river. So history of this: to meet the requirements of irrigation in Malakand Valley and district Mardan and Sawabi, an irrigation scheme was planned by the British government in 1903. So it is constructed by the British. The plan consists of headwork at Amandara near Batkhela on river Upper Suwat, unlined irrigation channel 7.2 kilometer long up to Malakand Pass, and excavation of 17.5 feet dia 3.4 kilometer long tunnel underneath of Malakand Pass. A network of irrigation canals including Abazai and Machai branches and their distributaries were also part of the project. The project started in 1907 and completed in 1914. So this Amandara headworks, you can see that these were constructed by the British government. Now you can see this information from this website here. These are the different pictures showing Amandara headworks. You can see the baffle blocks. The idea here is to dissipate the energy of the flowing water. You can see here the fish ladder which is provided here, and the water flows over this weir here with the shutters provided here, and this is the canal head regulator. So you can see this video. This is downstream of the river Swat. This is the upstream side. And this is the head regulator. This is the canal head regulator. You can see the fish ladder. These are the baffle blocks to dissipate the flowing water energy. For this, in case of floods, then the water can flow here also. This is the head regulator. This is Swat River. This is the head regulator.